And then Professor Amulan has introduced wind and seismic loads and how systems are kind of conceptualized, how its design is accounted for. But when it comes to establishing the system, you still have to use some of the technologies or techniques that we have looked at so far. I talked about some. Satya Seelan talked about quite a few what they have practiced, right? I want to show you some of the beam column joints that people have used in the past. This is again what they call an emulation type. It's used in both seismic and non-seismic, and obviously in the seismic region, they would expect plastification at the end of the beam. So typically, what you have is you have a column. If you imagine that the column is extending through here, as it's subjected to a lateral load, you would expect this region to experience maximum moment demand. So if it's a cast in place, what's expected is that this region will develop a plastification, like a simple cantilever I explained yesterday with how the yield penetration takes place. Now, regardless of how you design this, if you subject a system to the same set of lateral loads, the moment demand, so if it's a single bay, you would expect the moment to, so if this is a center line, the moment is going to go maximum here, maximum there. So the same thing as what I explained to you last time would happen as well, like what we discussed about what happens in the plastic inch region. So it's important to realize that when you detail this region, you don't put in any additional reinforcement. You don't unnecessarily strengthen that region by putting couplers or lap plyses and things like that. So the typical non-seismic details when was transported to seismic application, that's something people paid attention to, that we would strengthening the region doesn't get strengthened, so that if you strengthen this region, then the plastification will start to take place outside of where you think it's going to, or you envision it's going to take place, and that initiate other problems as well. We briefly talked about that. So you could see this particular detail was developed for seismic. They look at precast or cast in place columns, but the beams are prefabricated. So in this particular detail, you could see the beam is put in place, and all of this region, as well as the top part of the beam, requires in situ concrete. The advantage with that is that you could also do that topping with a slab so that it connects everything together, right? So in this particular detail, there are a few things I want you to observe. One is they have shear keys here. So those are things that you want to decide if you want to increase the shear resistance. So they included shear key in this particular detail. You could also see that it's got seated a little bit on the top of the columns. So they do that to eliminate any temporary support if they can utilize. Obviously, it's going to save time and money if you can temporarily support on the top of the column. And then they will do all of the casting with the cast in place concrete. That will be done after placing some top reinforcement as well as doing the formwork for the floor slab as well. Let's look at the other detail. There are several details like that, but the variations are very, very similar. So in this particular detail, everything remains the same except if it's what's happening into the joint region, the beam column joint region here. So in this particular case, they made the beam continuous. So beam goes continuous, but it could be continuous or it could be simply supported as shown here. But they've shifted the joint, the prefabricated or the joint for the precast elements to the less critical region. So, as I said, if the moment is going to be like this under lateral load, this region becomes less critical. It's almost zero moment. So that's where they shifted this particular connection. So therefore, that becomes less critical. Maybe this region is going to be acting more like a cast-in-place joint or cast-in-place beam column joint region. When you have this corner element, then you could also see how they are tackling with this L-shaped piece that comes in and establishes the connection in both directions as well. So all of that detail has to be worked out as well. Now, one thing I want you to realize is when we have the joint in either form, whether as shown here or as shown here, because the maximum moment is going to be in this region, that's where the failure is going to initiate. That will be the same thing applies to a cast-in-place system as well. The only difference is that with whatever the detail that you have accommodated to integrate the precast elements, it could potentially alter the behavior. Now, if you look at, so this section was to look at what has happened to precast building in the past under earthquake loading. So, as I mentioned yesterday, when it comes to precast, their behavior will heavily depend on how well your connection is. When I say how well your connection is, how robust the connection is, that's one question you want to answer. And the second thing you want to check and make sure is that has the connection modified the expected behavior of the precast system? Those two elements have been a concern for the code committees typically. So in the past, they didn't allow precast to be used in the construction of critical or buildings, what's considered to be designed for people in the public occupancy. It could be a school, it could be an apartment building. There was hesitant in terms of providing approval because they said, because you're connecting pieces together, what happens if the connections fail? Connection can potentially fail, and if it fails, then it could cause a lot of damage. It could it could cause injuries, and we could potentially lose lives. So those concerns were always there because they've seen in the past, cast in place goes through some damage, but they don't collapse. The most significant event that that exercised some of the precast building was in the 1994 Northridge earthquake. So in the 80s, late 80s onwards, what the committees or the courts allowed is you could use precast, but only for parking structures or less critical structures. Warehouses they allowed, parking structures they allowed. But the earthquake itself in 1994 showed that a lot of the parking structures actually failed quite a bit. So the committee members who are opposed to the idea of promoting precast members basically said, we told you so, right? So their concerns become more serious at that point. Some of these details that I'm showing here at the same time was actually developed in New Zealand, because New Zealand is an earthquake-prone area, at the University of Canterbury. They tested it, they felt comfortable with the connections. So in New Zealand, if you compare US or India versus New Zealand, the way they exercise is very different in terms of how they push new ideas into the design practice. New Zealand is a pretty small country. It's like, I don't know, they have now maybe 4.5 million people. So almost every engineer knows every other engineer, and they come together and make decisions and work with the industry and put it in the code and apply it. So especially in the city of Christchurch, they put in a lot of precast details, and the city was built with the concrete, mostly a concrete structures, but heavily used precast fabrications. So these details that you're seeing here were used in New Zealand. Here's a very different detail here. So what you see here is a precast connection with post tensioning, which is an attractive idea. So column is basically prefabricated, beam is prefabricated. There are ducts included here. What they do is they put the post tensioning. They will post tension it. So anytime you apply significant post tensioning, by friction you should be able to you should be able to provide resistance through friction, because the amount of post tensioning we put in for these systems are pretty substantial. So when you initially place the beam, you can see there's a temporary support is put in place. These are typically easy to integrate, so they will have maybe anchor point here. They will bring in a steel angle get attached to the column, so that then they can put shims and they can drop the beam in place, level it, they apply the post tensioning. They will also include what they call a grout or an epoxy pad or dry pack to make sure full continuity between the beam and the column. They would also, in addition to post tensioning it, they will also grout the tendon. So we talked a little bit about yesterday in terms of unbonded versus grouted post tensioning option. So keeping it unbonded will keep the system elastic. This particular detail was fairly popular in Japan. Japanese felt that this detail can work, and they prefer to use this particular detail. In other countries, people were reluctant to use post tensioning with the grouted details. Do you know why? What would happen if you use a grouted post tension? Anybody?
You cannot take away the strain.
What's that?
You cannot take away the strain. Right?
Yeah, that's one thing. You cannot replace it easily.
You could also start yielding.
Yeah, yielding will cause compromise, right? So, do you have the okay. So this is something you want to start thinking about when it comes to post tensioning, and we discussed this quite a bit yesterday. So if you look at stress versus strain of a post tension strand, let's say this is the shape. So this is, I don't know, something like 1860 megapascal. In these systems, what we typically develop is what's known as the strong column, weak beam concept, right? So the beam basically would rotate. So if I just isolate and look at one bay, let me just show this. So you're looking at a multi-story building basically, and so if you push on it, I think Professor Amalan talked about equal and static load this morning. You're pushing it, so the building is going to start swaying. All of these regions will develop plastic hinges. In order to distribute the plastification, you will actually allow the plastification to take place at all of these regions. And you do that by making this location to be weaker than the moment capacity or yield moment capacity in the column, so that you force this to yield. Okay? So you have yielding is going to happen at this location and at this location in the beam, so that the beam can rotate at these two locations. So if I use post tensioning, you would, let's say you apply some post tensioning value here. as it goes through deformation, this force will increase and go to somewhere here. Right? And then when it comes back, it's going to come along this path because you already yield at the post-tensioning steel. So it's going to come back here, and if it come back to zero displacement, what you find is that you actually lost your post-tensioning. So if you lose your post-tensioning, your connection become very weak, and it cannot resist the load anymore. So why did the Japanese prefer to do it? I mean, they said they tested it, and it's good enough. That was the argument they made. So this particular detail, what you see is, you will develop the plastification somewhere here. It will potentially yield here. So what happened was that, like what I said, when you develop critical strain in a rebar or strand at one section, it's going to spread. The adjacent section will have slightly lower strain and slightly lower strain as you go away from it. So what happened was that in this region, you basically damage the grout locally. As you damage the grout, because it becomes debonding, it became debonded in the localized region. So once it became debonded in the localized region, the strain is not concentrated. So the increase in strain is not going to go from here to here. Maybe it's going to go from here to here somewhere. So when you unload it, it doesn't lose that pre-stressing as you would if it's a perfectly bonded connection. So that was the reason that they were able to convince themselves it seemed to work fine, but they're basically locally debonding the connection, and that's the reason it was surviving. But that behavior is, it's very dependent in terms of the quality of the grout and how well the grout was placed, and whether they were able to get full bonding in that region or not. If it happened that if the grout at the local location is stronger and weaker in the other regions, the performance are very hard to predict. But the buildings will survive because this can happen. It will not go as bad as this. Now, from this step, when other researchers in the US and other countries looked at it, they thought, why are we keep bonding and creating this problem? So we should go unbonded. And so that concept was kind of started to look at the debonding, the completely debonding the strand for the entire length. The only argument, as I said yesterday, is the safety in case what happened if it break. But the technology is pretty good. Or you could, as I mentioned, partially bond the strands, if you prefer.
So even if it breaks, you may have multiple strands. There is a highly unlikely chance that all of them break.
Yeah, typically that's true. As I said, I think all I've seen so far is maybe not even strand break, but a wire broke for sure. One or two wires snapped. That's the extent I've seen it. But the quality of construction, the inspection, quality control, yeah, like Satya is very keen to use this. I said, first show me we have to test the strand. It's
far from desirability.
yeah, strand has to be tested to make sure that, so we can check the anchorage system, strands, and the ability to hold. Once that's established, then you can reliably use it. So Japanese kind of still went in that direction, and then they had the 95 Kobe earthquake. And between the two earthquakes, so in 94 earthquake in California, which tested some of the parking structures, which basically took the emulation concept and put it for a test, whereas the Japanese let their building go through this type of structures to see how well it performed. The Northridge earthquake, almost every parking structure within the certain radius of the epicenter basically damaged significantly. So I'll show you some of the damage of the structure. So you could see, let me see where the file is. Thought I had it. Defense. Okay. So this is a paper which I can share the paper with you. So this is the Los Angeles region. So all of these places recorded earthquakes. I don't know if the Northridge is marked. Northridge is in the Ventura County. So Northridge is right here. That's where the epicenter was. So there was two structures that was very well, like a lot of media coverage also took place. One is a parking garage at the Cal State Northridge, or California State University Northridge. And the second one is a parking structure at a shopping mall in Northridge. So that's what the fashion center parking structure looked after the earthquake. So you could see a few things I want you to observe, that the damage or the collapse was pretty significant, and you could see these columns are standing. The vertical element, you can see they all are standing, implying that the end region where the beam or slab or whatever supported or connected was, failed and just took the floors down without bringing the columns down. If the connection was supposed to be robust, then it should have taken the entire structure down, right? It should have moved sideways, or it should have collapsed and took the columns with it. So that kind of implies the connection didn't perform well. This is another view of so they had a big parking structure, and you could see the different side of the structure collapse in a different manner. So there's a partial collapse of the structure is seen here, and in this particular case, this column itself failed and took the floors down. So this is the column that used to support these two beams, as you can see here. One of the popular item is staircase. Precasters make staircase and attach them to the structures pretty successfully. So you could see that in this case, the staircase didn't come down. They stood pretty good. But most of the failure are related to the beam to column connections. The second structure that I want to emphasize, I want to highlight is this particular structure. So here's another parking structure. You can see this portion collapsed. This area has collapsed. And this case, the frame, you can see the exterior frame were well connected, but it was bent inwards because this region collapsed. So what happened here is that the columns within the structure failed and took the floors down, and that pulled the perimeter frame inside as well. So when they seen this damage, they said they will not promote emulation type connections in the US for other type of structures. They thought it should be looked at differently and come up with a newer system if you want to use precast concrete.
So that is, see, had this parking structures be cast in place, what failure would have happened?
So if you do a proper design following capacity design philosophy, then you may not have collapsed the structure. So you would have foam plastic hinges and it would have shown some damaged area, but it's very likely that structure would not have, completely given up, right? So, these are all indications that they were trying to develop. So, in all of these observed damage, what you see is that the structure is trying to behave like the strong column weak beam concept, because that's what kind of instituted, but the connections were not robust enough to hold on to it and eventually cause some failure. So the emulation concept, what we talk about emulation, is basically works fine in the non-seismic region. PCR handbook also has a lot of detail as to how to connect the pieces. Typically, those structures don't get overloaded, right? So unless you have a cyclone or earthquake or something comes along, the structure get overloaded. But then in those situations, you're expected to design differently. So the parking structure performance was not as great. In fact, it was a big failure for the precast industry. And people said, no, we're not going to even build parking structures using precast element at that point. In Kobe, there were actual buildings went through earthquake motion. They performed reasonably well because the post-tensioning is pretty reliable. They're bonded, so it's very unlikely that you will lose. But because of that plastification we talked about, the connection region did experience damage that they couldn't fix it after the earthquake. So even though structures survive, just like cast in place, they have to take the structures down. And there were concerns about localized failure. So because the spread of plasticity is not as good as what you see in a cast in place system. Go ahead.
Good question. So typically when we design for lateral load system, either you have heavy moment resisting frame to take the lateral load, and gravity frames are typically smaller in size, and in proportion to their stiffness, they don't take much of lateral load.
Correct.
In spite of all these things, how could the gravity load system can fail like this?
So what happens is that when you go back and forth, so the gravity load bearing columns are typically not expected to take, but the building doesn't know that, right? So when they go for the ride, these end regions are supposed to be pin-ended. They're not fully pinned. I mean, they don't put a pin through there. They do put, so they basically bring a steel plate connections. So they reduce the section dimension and then run a rod through. So that system will resist some movement. And if it doesn't go for the ride, you will start causing some damage in that region as well. Theoretically, they are pin connections. And if they don't move, in fact, one of the Northridge building, when they didn't move, then you lose members because they cannot, the seat that they provided is not large enough. So they lose the floor. If the perimeter frame was designed well, they will take the perimeter frame. That's exactly what happened in the Northridge event.
Typically, the precast is here, even for our gravity load system, only the beam connections are made shear connection. Columns are all monolithic.
Oh, I see. As a cast in place or as a precast?
Precast.
Yeah, so it depends on how, so country to country changes, so it varies, and the precasters decide how they want to do it. So they could do a continuous column with beam for each bay. You can do a continuous beam, or you could mix and match. So it's all depend on the transportation limitations and what precasters feel comfortable doing it and things like that. Dictate.
The point is, if at all we have to prevent this, then even for gravity load columns, the confinement is very important.
Yeah. So I think so yesterday we talked about the fact that you design components, but the system level check has to be done to make sure that the system, your structure can take the load and distribute and transfer down to the foundation. That's something you need to make sure that it can happen. So, yeah, there are a few structures in Northridge that has gone through. Some of the failures would have happened in cast in place as well, but people didn't think through as, so anytime a precast structure has gone through, they always point and say it's a precast problem, which is not true, which is an unfortunate situation.
These are short columns.
Yeah, so the short column issue is for cast in place also. It will show up, but nonetheless, they thought that precasters should address this issue as well. The Japanese earthquake, the Kobe, brought damage to the system, but it didn't bring structures down. But they were, Japanese tend to do two things differently. One is we all use capacity design. I don't know if Professor Amalan talk about allowing structures to basically go through inelastic motions, right? So inelastic deformation, so that structure can be designed more cost effectively. And by doing design in that fashion, it also helps you to limit the amount of forces goes into the system, right? So when a structure goes through this inelastic pad, the force can't increase, right? If it's an elastic pad, it can continue to increase. So that's why structures are designed. But the Japanese didn't quite appreciate that. They wanted to keep their structures more or less elastic. They thought they had a good handle on the seismicity. Along with this, caused a lot of damage in the Kobe earthquake. I think Kobe killed more than 5,000 people, to give you a feel for how bad that was. So after the Kobe earthquake, Japanese have decided they didn't give up on their post-tension connections as they have done it, but they added some rebars to provide some additional energy dissipation capacity. That's the modification they made. They also acknowledged that they're not going to design to keep the structure elastic, but allow some moderate ductility to develop. So they kind of brought in some. If you look at US and New Zealand, I think India also, we promote the inelastic action to develop, and so that the plastification will take place. There was an earthquake another country that used precast and experienced seismic loading is Italy. Italy had an event in early 2000, I think. Was it early 2000? They had multiple events, so let me see which. So this was, it's a 2012, it's a 2012 Emilia earthquake. So I'll share some of these articles and feel free to read through. I downloaded the paper in the Word or PDF version that is not copyright protected, so I can share it with you. Okay, so you could see in this case, I want you to just observe the two things I'm trying to do to show you how precasters have assembled system versus how well they perform. So they have a fairly different details here at the base. So the columns are put in a socket. So this concept has not been promoted in other countries. They thought the socket connection may not work well. There have been a lot of tests done in the recent time, mostly for bridge applications. And what we found is that typically they actually perform pretty good. But in this case, it depends on what this element is made out of. So if the socket is in a foundation block, and if you can make sure that adequate embedment into the socket, it actually performs pretty well. If it obviously is subjected to tension, you need to provide some ties into the foundation block. as well. So you could see how they assemble this structure. Double T's are used here. You can see they use cobalts here where it's supported. And this area, the roof is also kind of a tapered precast beam is what they used. So you could see the roof on one side. So this area, so again, observe that the damage or any distress occurred basically in the connection region. So that's a important piece to realize, that where you are connecting, that connection is going to be tested. So if you go back to this concept here, I said the concept here is that strong column, weak beam, meaning that the hinges are going to develop in the beam. Now transport that knowledge to a precast system, then the weak beam concept basically says the connection has to be weaker, right? But if you make the connection weaker, that connection should also have ductility or toughness. Otherwise, you're going to lose this connection. When you lose the connection, you will lose the system pretty quickly. So that's basically what we keep seeing it in earthquake world when these connections were brought into the seismic design for precast structures. So here's another example. So this is where the precast would come in. So you could see all of the damage would occur just in the connection region, not in the precast member. So whereas you go back to the regular cast in place, the reinforcement is continuous, and the weak region or the critical region become plastified. When that happens, the member is continuous, the connection is not separate or it's not added on, so therefore the performance appears to be better, even though locally that it gone through some de-stress and crushing and spalling of concrete. We'll look at some of the examples. So whether it was New Zealand, US, Italy, Japan, precast generally didn't perform well. And so this is when the concept of the press got started. So there was a program started in the US called Precast Structural Systems Research Program, basically stands for press. They went through 3 different phases of research. The first phases, they looked at conceptualized a lot of connections. So the idea there was, okay, let's not look at precast as it should behave like a cast in place, but how do we take advantage of the precast features and then promote better behavior? So let me open. So this is when this concept was kind of began. So this is what we were beginning to talk yesterday. So the bottom is what I talked yesterday, right? Where you cast in place. So you imagine you have a column or wall, cantilever system attached to the foundation. If you push on it, you're going to create, is that large enough? Yeah, so you're going to create this kind of a damaged region. When this damage takes place, what I want you to observe is that it produces this hysteretic response. So this area under this curve basically gives you the static hysteresis as an equivalent damping for your system. So the earthquake energy gets dissipated by this plastification. So when you do convert this area into equivalent viscous damping, you will find that this number is about 25 to 35% typical, depending on what you're testing. So going back to this test people have done from mid-70s onwards, they quantified and said, if you build structures with 25-35% range damping, your structure should survive. The concept was brought up for a cast and place system. If you look at this system here, this is a precast system. If you don't rigidly connect, allow this to basically rock at the corners, for example, one of the disadvantages is that your shape of the hysteresis will be different now, because you don't have the plastification or spread of plasticity as you see here, and therefore your energy dissipation is going to be limited. So the disadvantage is that you will have less amount of energy. The huge advantage is that as you load into the inelastic region, you come back, it actually goes through closer to the 040 displacement point. Implies that if by the time the earthquake is over, your building is going to be back to its original position. Whereas in the cast in place, that was not the case. So cast in place structure, whether it's a bridge or building or warehouse or whatever, once they go through large amount of inelastic deformation, they will be leaning in one direction typically. And when that happens, the choices are pretty limited. You have to take the structure down and rebuild it. But the precast, if you can use that concept, then one could appreciate that if the damage is limited, you can repair it and hopefully you can reuse it. So this concept was kind of looked at from what they call a free rocking structures. So in earthquakes, I think a well-known scientist Hausner came up with a theory for free rocking structures. So the free rocking structure behavior is very different than typical dynamic equation of motion concept. You have to you have to analyze it as a free rocking body. So free rocking structures will go through different motions than what one may call a control rocking, which I'll get into it some more tomorrow or so. So the question is, so I think it was earthquake in Greece, some earthquake in the other places, they found some historical structures, tombstone and cemeteries. Some of them didn't actually fall down during the earthquake because the free rocking was actually helping structures to perform better. So people have started to look at, okay, maybe there's something that we should look at it. But if you rely purely on free rocking, if the earthquake happened to be significantly large or the energy content coincide with the period of that free rocking body, then you may run into other problems. So you have to control somehow how far the rocking can take place. So the concept was kind of taken into the precast world for seismic application.
Here does PT stand for precast?
But just say that again?
No, the PT here stands for precast?
No, pre-stressing, unbonded post-tensioning, post-tension. Yeah, that's what you would have in a typical post-tension case. So that's kind of got started with the post-tension system, and so here is one of the first system that was studied, called hybrid connection for beam column joint. So in the hybrid connections, what you do is, this is precast, the beam is precast, this beam is precast, the column here is continuous as you mentioned before. So you bring the columns first, temporarily supported, then you drop the column in place, so they will have like a temporary support here, like a steel corbel, which could be attached to the columns on both sides. You can attach to the column and you support the beam. there are two set of elements get used to connect the system together. One is unbonded post-tensioning. The unbonded post-tensioning basically apply just like the Japanese do, except that the post-tensioning is unbonded. On top of that, you can see that there is a mild steel put in place. So the mild steel reinforcement it's a short rebar that basically goes through, it doesn't have to go all the way, but in this case, you can see from here, you can terminate it here or you can continue to the other side all the way here. That bar has to be grouted in as well. So when you apply the moment, so let's say if you move this beam, basically, tension develop here in the rebar and tension could potentially develop on top of the initial pre-stressing. Those two components will resist the moment. So the advantages of this, what they call a hybrid connection, is that the post-tension, unbonded post-tension promote the self-centering behavior, like what you see for free rocking. But by putting the post-tensioning in the middle, it actually limits the amount of rotation. So that's where the controlled rocking concept comes in. So you're controlling how far it can rock. The reinforcing steel, what happens is the reinforcing steel itself will participate. You can design them to go through inelastic action. If you do that, they will add some additional energy dissipation to the system. So basically, what you're doing is you're going back to this system, what we looked at earlier, conceptually. Whatever we have here, it will remain similar, except that we will increase the hysteresis loop to bring in more energy dissipation. Observe that if I have a tendon here, there's going to be a gap open up. This will be a substantial gap opening at the base. And so if I'm moving this, let's say 100 millimeter at the top, I'm moving this at the 100 millimeter at the top. Both from deformability point of view, these cracks, what you see here, these cracks will have different depth, different width. If I take the summation of that crack, that should be roughly equal to, same as this, right? But the disadvantage is that because this is a localized large gap, if I put in a rebar here, you will have large strain concentration at that location. So your bar will fracture faster than in a cast in place situation. So we overcome that by debonding the rebar locally. Debonding rebar is not difficult. You can put like a duct tape around it or grease it. There's a number of ways you can do it. So you also calculate as to how much distribution you're going to have. So you can control how much debonding you want to do, and therefore how much energy dissipation you will get out of it. All of that you can control. You can also decide between post-tensioning and the rebar, because both provide moment resistance, how much it should be resisted by post-tensioning and how much should be resisted by rebar. You can mix and match to establish your desired system. So go from precast emulation type connection. Now we are moving away from this jointed system where we are saying, okay, precast is going to have it's already have an interface here because there's a discontinuity there. So if you're going to open at that location, there's no harm in that. Advantage, my member is not going to crack, which is better than cast in place. That's a huge benefit. And I can provide energy dissipation. It's not going to be as much as cast in place, but I would argue that probably we don't need that much energy dissipation. So we did do a series of studies to see what would be the minimum energy dissipation I would need. And we were able to show if you have 8-10% range is more than enough. Current code, the ACI asked for 18%. Because they come from this world 25-35, so we brought it down to 18. So the document is being revised. My hope is that we can hopefully reduce it further to 12-15% depending on the seismicity level. So if you're in a high seismic zone, maybe you put in 15%. If you're in a low seismic, maybe 12% is more than enough. That's the thinking in terms of how it will come together.
Now, for some of this, I think the challenge that we face in India is testing will be possible. In absence of testing, are there models to predict all this?
Yeah, so the people have done quite a bit. So what has happened is that the hybrid connection, I'll show you some videos and how well these things perform. It performed really well. It performed really well in the sense it minimizes damage, it's self-centered, and it performs very reliably in repeated earthquakes. So it got attention from a lot of people. So this hybrid connection has been now transported to timber structure. People are designing, glue laminated timber columns and beam connected with post-tensioning and energy dissipation and things like that. Even steel structures. So the Northridge earthquake, when Northridge earthquake happened, concrete buildings did okay. Bridges performed poorly. Some of the bridges we knew was likely to get damaged in an earthquake. They were upgrading it, but earthquake came along before they finished the upgrading. So some of the structures experienced pretty significant damage. Precast performed poorly, but steel structures appear to be worked out really well, performed really well, and steel industry kind of celebrated the direction to go with steel structure. But in one structure, there was some floor damage, and they had to remove the floor diaphragm partially, and found that they used a lot of weld between beam and the columns to establish their connections, just like precaster will do. They have to establish those connections. Those welds were broken. And then they started inspecting almost every steel structures, and a significant percentage of steel structures actually experienced weld damage. So then that industry wanted to come up with a new plan as to how to deal with it, and they went through a series of experimental evaluation and established new connections. I think it's a program called SAC project. They reinvented as to how they should design structures for seismic. The end of that program, they saw what precasters have done, and they have actually took hybrid connection and applied to steel structures as well. And they have also built some structures with post-tensioning, and which surprised me with post-tensioning, to hold steel structures together.
That's really
Yeah. So the hybrid concept has gone quite a way. So all of these folks, the timber, concrete, steel, they've done a lot of modeling, trying to match the responses. So, you could do some.
This also was a 4-story or 3-story.
5-story building, yeah, we tested. So there's enough work has been done. But some of the, you can test just a column, a component of it. I think there's enough to model and start the process and look at what may be ideal for your system. You may want to rely more on the rebar initially, and it comes down to how well the grouting the rebar is not easy. Precasters have figured it out, so they have done it successfully. So we don't have that many structures, but in the US, I would say the hybrid system is in maybe half a dozen buildings. The same concept has been now applied to walls, and there are a few other things that develop, and we can continue to talk about different things that came along here. One of the things I want to emphasize is that when you see these connections, so for example, if hybrid connection works well and you establish it, even for non-seismic region, you can simplify that and use it, right? You don't have to, if it works out to be more cost effective, that may be a way to use it. Yeah, so let me just show you. So the hybrid connection was in a large scale used in this particular structure. So this is the one I mentioned yesterday. This structure is in downtown San Francisco. It's a 39-story structure, and the hybrid connection was used not only for frames, but they also brought this unbonded post tensioning through the corners of the structures to continue, so that the perimeter is exactly could be held together. So this is the tallest precast structure in the seismic region in the US, I would say. Tallest precast, 39.
Where in the US is this, sir?
It's in downtown San Francisco, in 3rd and Mission, if you want to go and find the building. Corner of 3rd and Mission. Okay, I want to talk a little bit, I think we have time, right? So I want to talk a little bit about some of the other stuff that even Satya talked about, and so you get an appreciation for. So the same concept has now been moved to wall structures as well, right? So you could apply the same concept where the post tensioning could be applied at the center of the wall, if you like, or if it's too much post tensioning, you can split them and put it in 2 different locations. The advantage at center, putting the post tensioning at the center, is that it will go through the displacement, or the uplift here is going to be smaller compared to here, right? So keeping it at the center has an advantage, but if you don't, you can also spread it. So one of the other things, I don't know how many of you in a cast in place situation, you have to have confinement at the base of the critical region, whether it's the base of the column, base of the wall, or the end of the beam, so that the plastification can successfully develop with large inelastic concrete compressive strain developing. In precast now, with the jointed concept, they basically rock at the foundation, so the impact to the elements over the height is actually not as long as what you would see in a typical cast in place. So you need to have some confined region here to take the impact, but they're not that significant. Now you see in this series of pictures, so these are different concepts that people have proposed. In this series of pictures, they put in these dashed lines. These are the mild steel reinforcement put in to create that hybrid concept where these mild steel provide energy dissipation. So it could be a system like this. The post tensioning provide the restoring force or the control rocking, whereas the mild steel provide energy dissipation. In cast in place, they both are connected together, right? You design the amount of reinforcement based on strength. By doing that, you already fix the amount of damping. You don't have a way to control that, because that inelasticity is what translate to certain percentage of inelastic damping. That damping is, all you can do is you quantify and say how much damping we have, and that's where the 25-30% number came about. There's no reason, nobody argued that you must have 25% or 35% damping, or nobody designed the structures for damping. They designed for movement resistant. Damping came along with it. In these cases, you can manipulate how much damping to put in, right? So if you want to have less damping, put less mild steel, more pre-stressing, or vice versa. Now, this is the other concept. So, one of the disadvantage with this system, including the hybrid system, though, the structure goes through limited damage, the members don't experience damage, your gap opens up, but the rebar goes through, the reinforcing bar goes through inelastic action. Because they go through inelastic action, they are going to be yielding and they're going to experience residual strains on the rebar. So if you want the system to be usable for the next earthquake, you probably must replace the rebar. And replacing the rebar either in a hybrid connection or system like this is not going to be easy. So even though it has a lot of features, people didn't really take advantage. So one of the systems that we looked at it was what they call a jointed wall. So in the jointed wall, I think Satya talked about similar concept for some of the applications they have done. So here is a one wall, here's the second wall, and the walls are connected together with series of some elements that has a capacity to dissipate energy. Now, if they dissipate energy, if they go inelastic, they're exposed, so you can replace those dissipation elements after the earthquake. And, fixing structures like that is not difficult. So if you have a magnitude 7 earthquake comes along, you damage the building or damage the connectors, even though there will be aftershocks. So typically I would argue that the post-tensioning should be designed so that structures can survive aftershocks without the couplers or without these coupling elements, and therefore you should be able to replace right after the earthquake and bring the structure back to its original condition. So the jointed wall concept was born, I think was something we promoted or we investigated in the PROS program because it was very, very attractive. People also have looked at, instead of they took the jointed wall and connected walls with a coupling beam with the damage occurring to the coupling beam themselves. People go in different directions, right? You have to, at the end of the day, decide which system should you want to use.
But this would be difficult to replace.
Yeah, so in this case also, they're actually relying on unbonded post-tensioning. So you have to remove the post-tensioning, top in a new beam, and do all of that stuff.
But that the replaceable jointed
Connection is attractive.
how does it exactly?
Yeah, I'll show you some videos. Yeah, I'll show some of the stuff. So this is some of the flow connections that people have applied. This mostly came from New Zealand in terms of how the hollow core slabs are attached to the columns. And one thing to realize is there need to be a continuity reinforcement here, and they would also use some kind of a topping to connect the floor slab to the rest of the structure. So this picture shows the jointed wall that we use in the PROS program. So you can see this is the wall system. So here is one of the wall get post tension, here's the second wall, and here is the connection region basically. So as you rock, I think Satya showed yesterday, as you apply lateral forces, each wall will rock on its base. And whatever the elements you put in go through deformation and provide additional resistance, as well as they provide energy dissipation capacity to the structure. One of the challenges with this or drawback of the system works really well, I'll show you some videos and things like that for you to see. One of the drawback is that if this is a cast-in-place wall, we would have built it as a single wall, right from here to here. Now you split the wall, it provides some features, some beneficial features, but you cut the system into two different systems. When you cut into two different systems, efficiency, moment resisting efficiency actually goes down, right? Because your lever arm get reduced, right? Let's say if I say this is, let's forget the connectors. I have a post-tensioning here, here's the compression. So this is post-tensioning, here's your compression. Let's assume this is L/2 roughly. So my moment capacity is P times L/2, and you have 2 volts, so you got P times L. It's the moment resistance for the entire system. If it's just 1 volt, then I would have had 2P here, or even just say you have 1P here and 1P there because you couldn't concentrate it. So let's say it's 1P here, second P is here, or you can say my 2P is here, whichever way you look at it, and then you have, that's your lever arm, which is L. So you have 2P times L versus P times L. So every time you cut the wall into smaller segment, your efficiency goes down. So all we are doing here is that we are changing the lever arm, and that changes the efficiency of the wall. So this became a, cast-in-place folks said, well, it's not as efficient as our system, and precast doesn't have the same efficiency. That means you have to put more walls of precast as opposed to a cast-in-place wall. That's when we introduce what we call a pre-vec, which stands for precast wall with end column. That's what's shown here. So I've looked at it and said, well, lever arm is cheap. I mean, it's free. You want to maximize it. So the best choice would be to keep the wall as wide as possible and put some end columns. By having end columns, what the advantage is that you can actually transfer a lot of the gravity load through the end column if you wanted to. You don't have to engage the wall. Wall can provide seismic resistance and shift the connecting element to those corners, those end region, and your efficiency come back again. So we studied this pre-vec system quite a bit as well. Just to show you how a force displacement looked like for a system like that, look at how the damping has increased. You see the hysteretic nature of the response, and you could see how when you unload it, the response goes through the initial 0 point, which is what known as the self-centering system. So these systems, you're taking advantage of the precast features. We are introducing new connections, we are improving behavior, everything comes with it. So the one thing that we didn't do here is that we didn't force the precast to behave like cast in place. I mean, that's something you should always keep in mind. When you go into the new system or you use UHPC or some other material, don't just create something and say, okay, I want this to look like this. It doesn't have to. Let me see if I can find yeah, so let me show you this. And are we doing with time? Where's time-wise okay, or take another 5 minutes?
Yeah, we can.
Huh?
We can.
Okay. Okay, so let's see. I think it's loading. Give me a second. Okay, so if you look at the system, so this is the original system, which I showed you. So this is a jointed wall with a connector in the middle. One of the other problem we found with this system was that the connector element that was used for that particular test was a lot more expensive. So people complain about that too. So the performance was good. This is the connector element they use. It's basically a U-shaped plate. So the U-shaped plate basically rolls on the side as you go back and forth. In terms of the response, it did produce pretty good response. But when we moved away from it, we decided that we will promote this Prevex system, and then we looked at a different connector. So here's a wall panel, this is a column. This is a very cheap system, so it's basically a laser cut O-shaped plate. So it's basically you take a steel plate and just cut an O section, and you can dimension the O section to come up with the desired feature. And so you could see it's welded here, and then it just goes through the deformation. The first test of this was actually done at Incri in Taiwan, where I had a joint grant with the earthquake facility. So here's what we built, and the blue columns at the end are the end columns, and then the wall panel is just a single precast unit. So you could see when you exercise, it basically just rock back and forth. Your connectors are here, which I think the next video will show you clearly. There's no damage take place. It goes back and forth, and this is your natural joint interface, and it just rock about that one. So this test was done like a quasi-statically. So it's a slow test, but we were able to quantify the behavior. So you keep pushing into the larger displacement. We designed the post-tension to remain elastic, even when they go to a large expected displacement, and the performance was pretty good. Now let me show you the next video. This is basically looking at this base of the wall where you can see actual rocking as well as how well the connectors perform. So you can see the O connectors. So they were restrained so that they don't go through outer plane buckling. So they basically deform and provide energy dissipation. The wall basically rock back and forth, post-tensioning in the middle, and you can see there's no crack, no cracks opens up in the wall panel. So that particular behavior, so this wall was designed to provide same resistance as a cast-in-place wall we tested, which also performed fairly well, dissipated energy. But if you look at after 3% drift, both of the walls at the maximum displacement, that's what they look like. So that's a cast-in-place, because you develop multiple cracking, so which you see here, so there's a cracks develop and plastification takes place, whereas all of the deformation is concentrated here. And typically when wall goes through, if you have a floor attached to it, the floor actually gets uplifted as well, right? Floor will go up as it grows. I mean, because of the plastification, the wall will grow vertically, and your floor will have to go for the ride as well. So you will have a system, if the floor is getting elevated at the wall section, in other places it will not be elevated, so the floor has to go through that deformation. So some committee members in ACI argued with us that because we are developing a large gap at the base, The question was, what's going to happen to the floor? Well, I said it should be the same as what the cast in place, but cast in place is not a concern. But what we did was we actually measured at the first floor level how much upward movement we get. Turned out that upward movement here is actually smaller than this. Because these cracks, as every time it crack opens and closes, the debris goes inside, right? The crushed concrete. So they don't completely close. So each time they actually grow more. It's not significant, but so we pushed the problem to, it's a seismic problem, it's not a precast problem, it should be looked at. So from there onwards, we actually did series of tests, which I will discuss that tomorrow, which is to look at more things related to prevec. One is to understand the floor interaction, so how well the floor interaction will take place with the prevec. Should we rigidly connect? Should we isolate the floor interaction? What is the additional resistance that will come if the floor interaction was accounted for? So when we do seismic design, again, it's not precast problem. For any buildings, we don't account for the resistance coming from the floor to whatever the system that you're using and the interaction. In this analysis, we've shown that it could be as significant as 30–40% more resistance will come into it. So that's something people have to pay attention. It's not routinely done. It's will show up as a problem in the future, but it's something that should be looked at. So that's one thing that we want to look at. We also wanted to look at dynamically to see how well the system will perform, as well as the amount of dissipation that takes place because of the rocking. How well can we understand the rocking behavior? And then we also want to look at the damping element in terms of how little damping can be used to get away so that structure perform better. So which I'll go through that tomorrow. I think we're going to have another session from an industry member. Any questions?
So this was done numerically.
This is done numerically, but we actually have done an experimental work as well. We wanted to get a feel for how important the problem is, right? These are, again, we looked at it for precast system, but it's a problem for any structure, whether it's a steel or concrete or cast in place or timber or whatever, right? They go through the interaction, but code doesn't recognize that. You isolate and design, but when the structure behaves, so our concern is that if he claimed that this structure is going to be self-centering, so you could see it's not quite self-centering, it's not really concerned. We've looked at that and argued why it's not a concern. We will talk about that tomorrow. But if the floor interaction comes in, the strength goes up, and then you will have a larger residual displacement. Yeah. So even though you have a self-centering, walls in the structure may not self-center. That's what you solve. You basically sell to people. You have a self-centering structure. It's not really, unless you account for this.
This O-ring that what you're talking about, how easy is it to replace?
But
the O-ring that...
Yeah, it's very easy, right? So, so if you look at it, so the whole purpose, the purpose of this prevec system and this O-ring idea is that this is a steel column. This is a concrete column with a steel plate here. This O-ring is attached with well here and well here. You just remove the well and the O-ring comes out. And put a new O-ring and then weld it together. It's easy.
Again, yeah, this was a concrete column, still you put steel plate embedded.
You can put an embedded plate and then you can do the same. We actually tested it with the concrete column also. It works really well. Just to give you, I think this is, I'm going back a few years ago, the U plate that we tested, I think it will cost you like $500–600 a piece. This is like $20. It's just a big difference. It's just cutting the plate is easy, especially these days people use laser cuts.
Yeah.
You just give them a dimension, they will just cut these rings. And you can manipulate how much resistance you want by varying
It's a
the...
mild steel plate.
This is a mild steel, that's a stainless steel. Because that goes through a much larger strain, so they prefer stainless steel plate. And stainless steel plate, I don't know about here, but if you're welding a stainless steel to a embedded regular steel, then you need to have a specialized welder and a specialized inspector. Cost just keeps going. This is just simple as just adding plates. So we add the plate both sides, and then so stability-wise, it's keep things together as well. Any other questions, comments? How many of you are just ready to do precast? Because I'm seeing everybody's okay. All right, I'll stop here and then we'll continue tomorrow. And then we'll have somebody else talking
Yes.
after the break.